Hello, this is Aishi Pramanik. Today I'm gonna take you through my internship project, which I did in Germany. My role at University of Bremen, Germany, was to work on the research project uh, titled "Trading of Gate Count and Gate Depth Using Quantum Circuit Transformation." I worked under the supervisors Dr. Rolf Tretzler and Dr. Philip P. Newman in Computer Architecture Research Group. My work during this summer internship included a thorough research review and proposing a novel circuit depth optimization methodology and performing the relevant experiments to implement this idea. So, quantum computing sounds very exciting, right? Now, quantum computing is still in its infancy, and there are many challenges ahead, including the ability to build large-scale quantum computers with sufficient processing power. Quantum computing is basically a quantum computer science method that uses the properties of quantum physics like entanglement and superposition to solve real life problems that would be too complex for today's computers to solve, right? Moving ahead. Now, these are the outlines for my project. So I'll be discussing each and every topic. I'll delve deeper into this topic one after another. So please stay tuned. Now, why quantum computing? So the first thing which comes to our mind is that we were happy with our classical computers, right? Now, why all of a sudden do we need to introduce this idea of quantum computing? So what makes this quantum computers different from classical computers? So in classical computing, we have two classical bits, 0 and 1. So there are only two possible states, 0 and 1. Suppose we have a 4-bit number, then there would be in classical computing system, we will be having 2 to the power 4 16 combinations, right? But out of which only one will be used at a time. As opposed to this idea, in quantum computing, we have qubits. Now, what are qubits? Qubits are the entity, the smallest entity of quantum. It's just like a binary bits, It's analogous to our binary bits 0 and 1. Qubits are basically quantum bits, but the beauty of these qubits is that they can be of any proportions of both the states at once. And this is the here we introduce the concept of superposition, right? Superposition means that if qubits are in superposition, then and we let's say we have 4 qubits, then we can generate 2 to the power 16, 2 to the power 4, sorry, 2 to the power 4. There are 16 combinations and we can use them at once. And these qubits could be in a mixed state. These 16 qubits are possible, unlike in case of classical computing where there was only one state possible. Here 16 possible states are there, right? And because of this superposition there is some probability factor that like superposition means before you measure a quantum quantity, it can be of any proportion of any state, like it could be 10% 0, it could be 90% 1, 40% 60%. In this ratio there could be a mixed state, right? Okay, so for n qubits, this way we will be having 2 to the power n number of qubits possible combinations, 2 to the power n, and which is huge. And this brings us to the next slide. Quantum computation, a new computational paradigm, right? Now, let us look into the advantages of this quantum computing over this classical computing. The first advantage would be excessive speed ups, right? So there are some specific problems which a normal, ordinary, conventional computer cannot solve, such as integer factorization, database search, and some simulation of drugs. So as from this figure, as you can see that as the number of qubits increases, the the execution time, here the y-axis represents the execution time, but the execution time actually decreases. And this graph, this is an exponential curve, and this reflects the exponential speed up over classical computers. So as the number of qubits increases, as I told you, okay, 2 to the power n is a huge number. Exponentially this speed up also increases, and it beats the classical computers, right? And the execution time, as a result of this, execution time significantly decreases, right? Now moving on to the next slide. uh, let's have a look at now quantum circuits and quantum gates. Now here we will discuss one qubit quantum gates. What the single qubit quantum gates operates on single qubit. For example, NOT gate, Hadamard gate. Just like our digital gates, we have NOT gate. NOT gate is acting like an inverter. It is converting from 0 to 1 and vice versa. Hadamard gate is a special type of gate, especially in quantum computing, quantum computation, where it is used to create superposition effect between this 0 and 1, right? As from this picture also diagram, this is clear. If we have a state 0 and we pass it through the Hadamard gate, the output could be in a combination of, in a mixed state of 0 and 1, right? Next is our 2-qubit quantum gates. So let's have a look at that. So 2-qubit quantum gates means this operates on 2 qubits. Examples include C0 gate. C0 is controlled NOT gate, just like our XOR gate, and it's just analogous to our XOR gate, where this X is the X bit is the control and Y is the target. Similarly, X is control here, Y is the target here. So for our control input X, if when the control input is 0, this is remaining unchanged, the output is remaining unchanged, y it is equal to Y. So 0 to 0, 1 to 1, but when the control is 1, then the output is getting inverted. 0 becomes 1, 1 becomes 0, right? Now moving on to the second type of gate, that is swap gate. It is again another very important gate in quantum computation. So this swap gate, as the name suggests, swap, so swapping. So we are taking 2 qubits, and if we want to swap between these 2 qubits, if we want to swap these 2 qubits, what we will do is we will use this is represented by this symbol swap. And this is equivalent to, we have to remember one thing, that any kind of gate consists of this elementary C0 gate. The basic gate is a C0 gate, right? So this swap also is equivalent to the combination of 3 C0 gates like this. Now moving on to the next this topic, that is a 3-qubit quantum gate. This is another very crucial gate, Toffoli gate. This 3-qubit quantum gate is known as Toffoli gate, which we will frequently use throughout the discussion, and also our project is based on this gate only. So Toffoli gate. So Toffoli gate is basically, see, we are taking 3 qubits A, B, C, where A, B are the 2 controls represented by this solid dot, and this is my target qubit, right? Next is my IBM Q20 architecture. Now, IBM is a company which works on this new paradigm of computation, quantum computing, and they have introduced a Q20 architecture. This, just like our computer architecture, we have this arrangement of these qubits. There are 20 qubits from Q0 to Q19. Scientists are working on this particular computer architecture, this particular quantum architecture. So yes, so this is the Q0. From Q0 and Q19 we have in total 20 qubits. Now we have to notice a few points here very carefully, that this from this figure, as we can see, that this qubits Q0, Q1 are connected with this kind of arrow, and Q1, Q2 connected, similarly Q1, Q7, Q2, Q7, but you see that Q0, Q6 and Q1, Q5 not connected, and many such pairs exist like Q11, Q15, they are also not connected, right? Now this brings us to a problem, a challenge, and that is why we need quantum circuit optimization. So uh, the quantum circuits are bound to follow, are obliged to strict topological constraints. These are called so-called nearest neighbor constraint. This nearest neighbor constraints, which require that the computing entities, qubits, have to be close to each other in order to be able to apply a quantum operation or a quantum gate on them. So it says that we cannot directly apply a quantum gate on Q0 and Q6 because they are not following the nearest neighbor constraint, right? So first they have to be in close, but we can apply a quantum gate between Q0 and Q5 because they are in close proximity. They are following the constraint. But this Q60, Q6, or Q1, Q5 pair, they are not following this constraint, and consequently we cannot apply any quantum gate operation on them, right? So that is why, to satisfy this constraint, a circuit transformation is usually required to execute a quantum circuit on a particular quantum computer, which induces a significant overhead, right? This overhead can be calculated in terms of gate count and the circuit depth. Now, while in the literature, this overhead had mainly been evaluated in terms of gate count. In this research project, the resulting circuit depth has also been taken into consideration. So we have taken account of this circuit depth as well as the gate count, right? Now what is gate count? Gate count is simply just total number of quantum gates, and just analogous to our digital design. We want our digital design to have lesser number of gates as well as low circuit depth. Now what is circuit depth? We haven't come across the term circuit depth in our digital design, but we are well familiar with the term called delay. So it is more like the circuit depth is more like the delay concept. So what is circuit depth? Circuit depth is the time required from input to the output. So as the number of stages increases, the circuit depth also increases, and by making the circuit parallel, we can reduce the circuit depth. It's just like the parallelizing the digital circuits. We can reduce the delay, right? Delay, the time taken from the input to the gate delay, the net delay, these concepts, right? So it's basically delay. So uh, from this figure it will be more clear to us how this what we mean by the circuit depth. So from figure A, as in figure A, we can see that we have 4 qubits, right? And this is a swap gate, another swap gate. So this is like stage 1, stage 2, stage 3, stage 4. I guess you can see my cursor mouse pointer here. So stage 4 and stage 5. So there are 5 stages. So circuit depth is equal to 5. Whereas in this case, in figure B, we have, if we take this H, this is as this, consider this as a single entity, then this and this are now in parallel. So these are happening in parallel at the same time. So this is stage 1, this is again stage 2, and stage 3. So the circuit depth has been reduced to 3, and our aim is to come up with some algorithm which can significantly reduce the circuit depth as well as the gate count. So there has to be a trade-off between a circuit depth and the gate count, right? Moving on. Now, this Toffoli equivalent of Clifford+T circuit, as previously in the previous slides, we have discussed about the Toffoli gate. Toffoli gate is a 3-qubit gate, and it has got 2 controls and 1 target qubit, right? This is very important kind of gate. Now we want to map this Toffoli gate. If we want to map our Toffoli gate into the actual quantum hardware, this is the mapping Clifford, and this is popularly known as Clifford+T circuit. And this is a very famous circuit in the that we studied in the literature while doing the literature review. Because of many reasons, scientists prefer taking this Clifford+T circuit. Now this Toffoli gate can be mapped to this. Now we implemented this mapping on Python. Now as you can see that these are 3 qubits, and these are some gates, and let's focus on one particular gate, that is C0 gate. Okay, now the point here is that we have 3 qubits. Now our target is my job was to generate a Toffoli template. Toffoli template means for this cube, 3 qubits could be any three arbitrary qubits on this on this Q20 quantum architecture from Q0 to Q19, as I already showed you the architecture. So we have 20 qubits. Now these 3 qubits could be a combination of any 3 qubits, 0, 1, 2, 3, 2, 4, any random. So we will consider all such combinations and we will generate the number of the corresponding number of gate count and the as well as the gate depth. Okay, gate depth in the circuit. Now as we know that this is equivalent to this kind of C naught gate, so now we have to apply, at the end of the day we have to apply this perform this C naught gate operation between this two qubits, this and this. Now, so Q0 and Q6 are these two qubits do not follow the nearest neighbor constraints. So, and we want to perform a C naught operation between this Q0 and Q6. And how do we perform that? So first we have to do the swapping. We have to bring this to Q0 to Q5, and then this C naught gate. We call this C naught gate native C naught gate because they are following nearest neighbor constant, so which is present. So this is native. These are native between Q6 and Q7. We have native gates, right? Now our target is to implement the C naught operation between Q0 Q6 non-native gates, right? So here that is what we have written, that aim is the C naught operation between, let's say this is C, let's say 1 and let's say 0 and 5. So this is 0 and this is 5. We have to perform an operation between 0 and 5. Now we are just focusing on this particular C naught gate. Now this is C, this is control, this is target. Then how do we do? The aim is to do the C naught operation between C and 2, but they are not following the nearest neighbor constraint. Then what is the solution? So this C dash and T dash, this is native C naught gate. So C dash T dash following nearest neighbor constant. So these two are native C naught. So this is the native C naught gate available here. Now we have T, we have C, so we will try to, this A0 A1 are just our these are called ancilla bits. Ancilla qubits means these are just auxiliary bits, qubits, or just helping qubits, just to store qubit values temporarily, right? Now our target is to bring this T down to T dash and C up to C dash. Okay, then C goes here and T goes here, and then the native C naught operation is possible. And that is how we implement the C naught operation. And this, as you can see from this figure, that this looks like X pattern. That is why the name X pattern realization of the C naught gate. So this is the now why X pattern realization, as you can see from the figure, that this looks like X pattern. So our target, so whenever we are performing this algorithm, we can closely observe one thing, that this C dash and T dash is somewhere in the middle of this whole thing. Like this distance from C to C dash has to be equal to distance from T to T dash. So this is in the midpoint. These two are in the somewhere in the midpoint. Okay, so that the midpoint, because that is how the number of stages, if it is a midpoint, then the number of stages can be reduced, and if the number of and we can make use of this parallelizing concept, so we can make the circuit more parallel, and this number of stages got reduced, and you see that here 1 2 only 3 stages, and this later after this is what we are doing, the restoring operation. So restoring the original qubit values, because already we have done swapping. Now we want to restore the original qubit value, right? So that is why we have considered this X pattern for our project, and we have designed an algorithm which implements this kind of X pattern realization. Okay. Now what is swap gate optimization? Now this swap gate, this is the swap gate. Now we are considering this each swap gate. Now as I told you that the elementary swap gate consists of elementary C naught gates, and this is the combination of these C naught gates, right? So but you can see that if these swap gates are consecutive to each other, then we can do some extra saving of these gates. How? Because for each swap gate we have 3 C naught. Then for 3 swap gates we will be having 9 C naught gates. But here, as you can see in this picture, we only have 6. So we have been able to reduce three CNOT gates, right? So the gate count has also been reduced, incorporating the idea of swap gate optimization in this case. So first of all, we reduce the depth count, the depth, and then the circuit depth, and then now the gate count, right? And this whole picture is the X pattern realization of this particular small C naught gate, the X pattern realization of the C naught gate, incorporating the swap gate optimization, we get this final picture. And as we final figure, and as I already told you, A0, A1 are ancillary qubits or just temporary qubits. These are just holding temporary qubits. Cool. Now, apart from this, we also looked into T-depth reduction mapping. Now, we talked about circuit depth. Now, what is T-depth? T-depth is another important metric, another important parameter. And in quantum computing, it is very important to also throw some light on T-depth, means to reduce the T-depth. So, we have T and T-dega. These are the two gates. So, you see that in this figure, in the first figure where my mouse pointer is, the T depth is 1, stage 1 and stage 2. We are only considering T and T dega, right? T and T dega gates. So the T depth is 2 here, whereas in, 3 here, this and this. So 3, the T depth is 3 here. But in this mapping, which we already implemented, but in this mapping, using one extra ancilla bit, which is in zero state, which is at 0 state, the T depth has been reduced to 2. This is one T depth and this is another. So T depth is 2. So we have also implemented this concept, this kind of mapping. Now moving on to multi-control Toffoli gate mapping. So we extended our idea from this this is two control Toffoli gate, to multi-control, where the number of controls is 4. And we also did the same thing for number of controls equal to 3. And this is the kind of mapping we used these two cancel bits, and we generated the Toffoli template for this mapping as well, for MCT multi-control Toffoli gate as well. Right. Now our work and implementation. So we implemented the X pattern algorithm on Python. We used Qiskit Python, which allowed us to work on the real quantum hardware, to access the quantum cloud. And then we generated the Toffoli template, considering the T depth as well. Then it resulted in a significant reduction of gate count as well as the depth. We implemented the algorithm for multi-control Toffoli gate 2. Now let's have a look at some demo figures which we obtained from our algorithm, from our implementation. So first we have been able to implement the optimized X pattern realization C0 between Q0 and Q2. So between Q0 and Q2 we want to perform C0 operation, but since these two qubits are not following the nearest neighbor constraint, so swapping has to be done between Q1 and Q2. So Q2 goes here. So between Q0 and Q2 we have the connection. So C0 operation, native C-gate is possible. And similarly, we did the same thing, and we have shown the result for optimized X pattern realization of C0 gate between qubit 0 and qubit 3 for that quantum 20 architecture. And here optimized X pattern C0 gate between Q0 and Q4. And here comes the Clifford+T realization, the mapping, the entire mapping of two controlled Toffoli gate with controls at qubit 0, 1 and target at qubit 2. And these are two references which we have taken. The reference includes the research paper whose author was Dr. Philip P. Nierman, my supervisor himself. And so that's it. Hope you like this video. Thank you. Thank you so much. Have a nice day.